So in this unit, we're going to be looking at conservation of momentum. So we're going to have to apply the concept of conservation of momentum. So just like conservation of mass or conservation of energy, momentum is going to be conserved when objects collide. Okay, we're also going to need to differentiate between elastic collisions, inelastic collisions, and explosions. That actually won't come until a little bit later when we finish the energy unit. So first off, we need to describe what a closed system is. Okay, a closed system basically has no external forces that are acting on the system that aren't already balanced off. Okay, so this is the same concept that we'll see again in conservation of energy in the unit coming up. So for example, I have two cars colliding. Okay, I have a big massive bus and a smaller car. Okay, so even though we have two different objects, okay, with wildly different masses. Okay, remember, Newton's third law says that the force of the bus on the car is going to be the same as the force of the car on the bus. This is a concept that people usually struggle with, okay? They think the bigger bus will provide a greater force, but it's going to be the same force. How they react to those forces is going to be different. Okay, for a counterexample where it's not a closed system, I have a ball hitting a wall. Okay, the external force in this case is the wall acting on the ball. Okay, there is another external force that we don't ever really talk about. Okay, why does the wall not move? Okay, and that's because the wall is anchored in place. Okay. So what is a collision? Okay, when two or more objects hit each other, okay, and they're acting as a closed system in the sense that there are no external forces that aren't balanced off. Okay, so gravity, the force of gravity, is normally going to be balanced off with the normal force. Okay, so I don't really care about those two forces in this case. They're not part of my system. Okay, so there are going to be three main types of collisions. I'm not going to really quiz you on that on the types in this unit until we talk about energy in the upcoming unit. Okay, but the three main types that we're going to be dealing with are elastic collisions. Okay, in an elastic collision, momentum and kinetic energy will be conserved. Inelastic collisions conserve only momentum. Okay, some of the energy is going to be transformed into other forms. The last type of collision is actually not really a collision, okay, because the objects start together but end apart. And that's an explosion, okay. In all three of these cases, momentum will be conserved. Okay, the difference is whether kinetic energy is conserved as well in the elastic, whether I lose energy, kinetic energy, in the inelastic case, or I gain kinetic energy in the explosion case. So, conservation of momentum. Why do we have it? Okay, in a closed system, momentum is conserved, or in other words, the change of momentum in the first object is going to equal the change in the momentum of this, or the change in the momentum of the first object plus the change in momentum of the second object will equal 0. The form that we usually use it in has it as the sum of all my initial momentum, so the momentum of object 1 plus the momentum of object 2 plus etc. etc. The sum of all of those momentums in the beginning equals the sum of all those momentums at the end. Remember, the sum as vectors in the beginning equals the sum of momentum as vectors in the end. The reason this is true is because of Newton's third law, which states that all forces occur in equal but opposite pairs. Okay, so the magnitudes are equal but opposite in direction. Okay, so let's examine a collision in detail. I have a ball, the orange ball moving and colliding with the white ball, and after the collision, the white ball keeps moving, but the orange ball has now stopped. Okay, they do not need to be at rest, so we'll look at an example later. Okay, but before the collision, the momentum of the first ball is just P1 initial. Then the second ball is P2 initial. Doesn't really matter what those values are, okay? Just understand that they both have momentums. It may be zero, but they have a momentum. During the collision, okay, the impulse on the first ball, okay, the white ball creates an impulse on the orange ball, and the orange ball creates an impulse on the white ball. So that collision, or that impulse on the first ball, is the change in momentum of P1 is going to equal the force of object 2 on object 1 times time. And the impulse on the second ball is the force of object 1 on object 2 times that amount of time. But F1 and F12 and F21 are related by Newton's third law that says the force of object 1 on object 2 is equal but opposite to the force of object 2 on object 1. And since our time of collision is the same, okay, it says basically that the impulse on the first ball is going to equal the negative impulse of the second ball. Or since impulse is the same as change in momentum on the first object equals the change in momentum of the second object, but negative. Okay, so after the collision, I have P1I plus the change in its momentum, plus P2I plus its change in momentum. Okay, that's going to equal my initial momentum because the change in momentums, okay, cancel each other out. So because delta P1 equals minus delta P2, this and this will cancel each other out and give me 0. Or basically, after the collision, my momentum is exactly the same as my initial momentum, whatever those numbers happen to be. Doesn't mean the exact values, okay, the momentum of the first object is not going to stay the same, and the momentum of the second object, it's just that the net momentums will be the same. So here I have an example, okay? I have a 250 gram ball, so again, careful because that's not in standard units. Okay, 250 gram ball is moving to the right at 4 meters per second when it collides with a 1 kilogram, okay? So this one is in the correct units. 1 kilogram ball that is at rest. Immediately after the collision, the smaller ball is moving to the left at 1 meters per second. Okay, so be careful. So this one was initially moving to the right, and afterwards it's moving to the left. So that's where the vector nature of momentum and velocity is going to come in. The question is, determine the velocity of the larger ball after the collision. So here's the solution, okay? We're going to need to first calculate what our initial momentums are, okay? For the first one, it's the mass times velocity, or positive 1 kilograms times meters per second. The second one's at rest, so my momentum is just 0. So the sum of my initial momentums is just 1 plus 0, or 1 kilograms times meters per second. 1 kilograms times meters per second in the positive direction or to the right. My final momentum, okay, for the first ball, I know that because I have its final velocity as well, is 0.25 times minus, okay? So that's where the leftward nature comes in, okay? Because left is in the negative direction. So I'm going to need to keep that, okay? So that minus 1 meters per second times the 0.25 gives me a final momentum of minus 0.25 kilograms, or 0.25 kilograms in the negative or leftward direction. I don't have a velocity for my second one, so I don't have a momentum for my second one. That's what I'm trying to find out. Okay, so my final momentum is just going to be 1 kilograms times V final for the second ball. Or, you know, because it's just 1, it's just V final 2. So the sum of my initial momentums is 1. Okay, so here's that 1. And that's got to equal my sum of my final momentums, or the minus 0.25 plus the 1 times V final 2. Doing a little bit of algebra, we find that the final velocity of the second ball is simply 1.25 meters per second in the positive direction, okay, or 1.25 meters per second to the right, okay? And we're going to be doing a lot more analysis on conservation of momentum in class. Thank you.